Right, this is 9.8 power series, part 2. Now, let's recall for the power series, it must has the form, the x minus a to the n power, okay? Then we have three possibilities. We can go over some of these examples here. Find the interval convergence and the radius of convergence for the following series. Right, number one, we have the series. You see, you have x minus 3 to the uh, n power. So first of all, if you were asked what is the center of this power series, the answer is 3, x minus 3, right? So this is the power series center 3, okay? Let's do, okay, so what test will you do? Ratio test, okay? So always ratio test. The endpoint, we have to do it differently, but you always start with the ratio test, regardless of what formula you've seen here. So we use the ratio test. All right, so for the ratio test, we're gonna take again the limit, the absolute values of a sub n plus 1 over a sub n and approach infinity, and that translates into is the absolute value bar a sub n plus 1, so the n become the n plus 1 factorial, and then the over the n plus 1 to the fourth power time the x minus 3 to the n plus 1. It's actually on the numerator, right? So let me put this on the numerators, okay? And then we multiply by the reciprocal of a sub n, and that would make the n to the fourth stay in the top, and the denominator will be n factorial, and then x minus 3 to the n power, and that's in absolute values, right? So we have absolute values. All right, so let's say, what do we know? If you look at the cancellations of common factor, we have quite a few things we could do. One is the factorial, the n plus 1 factorial over n factorial. So again, the product's the same except the n plus 1 left. Okay, so except the n plus 1 left there, right? And then what else I can do? You see the power, that's to the n plus 1, that's to the n. So we have these two could cancel, and what's left is an x minus 3 factors there, right? So the n to the 4th and plus 1 to the 4th I cannot cancel. And if you wish, you can cancel further. I think this one and that one we could, but anyway, I'll just leave it there. Now the absolute, these are the positive, so you can n plus 1 n to the 4th, so those are the positive term, positive factor. So n plus 1 times n to the 4th over n plus 1 to the 4th power, right? So n approach infinity, and we have x minus 3. So put the absolute values of x minus 3 there. Notice that I don't put the absolute value there because the absolute of these positive numbers is still the same. If you want, you can do that, but we don't need to. All right, so now looking at this limit and approach infinity, The numerator, if you multiply it out, you see this is into the fifth power, that's into the fourth power. So numerator has degree larger than denominators, therefore this will approach infinity. So what is this limit? Well, now that's approach infinity, that means getting larger and larger and larger. So your limit will always blows up to infinity except for, so be careful. It's not always infinity, because if x is 3, then you got 0, so time anything, right, is going to be 0. And therefore, the limit here that we just calculate is infinity, okay, infinity except for x equal 3. So that means it will be infinity as long as x is not 3. And because it's infinity that's much bigger than 1, so we can conclude the series that we are testing right? The series always diverges, right? Infinities. So because that is more than 1, always diverges, except when it converges when x equals 3. That is when you got 0 for the limit, smaller than 1, so it converges. So the series here converges only at x equal 3. X equal 3. So the interval convergence is just a single point, right? And then for the radius of convergence, in this case, we say the radius convergence 0. That is actually our case 1t. Radius convergence 0. The series converges only at 3, which is the center of the power series, right? Now let's look at number 2. For number 2, we have this alternating series in the negative one there, but still we're not using alternating series test. We still use the ratio test for all of them. Okay, we use a ratio test for all of them. Now the example 1 here, there's no endpoint, so we don't have to do that. And let's check it out for number 2. If you do the ratio test, again, it's a limit and approach infinity. We have the absolute value bar. What's a sub n plus 1? Replace n with n plus 1. I have negative 1 to the n plus 1 plus 1. That's n plus 2. And see down the denominator, so that's a numerator. I'll put it on the numerator. That's x minus 1 to the n plus 1 over, and then you n plus 1 there. Then we multiply by the reciprocal, and the reciprocal would be n on the top over, we have negative 1 to the n on the bottom, and the x minus 1 to the ends on the bottom as well. Again, that is an absolute value bar. Once again, when you use ratio test, you can simplify when there is an exponential, see x minus 1 to n plus 1 and x minus to the n. So they cancel out. You're left with an x minus 1 left here. So these two we can actually cancel too if you want. It basically, but remember these negative 1 to the power either negative 1 or positive 1, either negative or positive 1. However, inside the absolute values, they all become 1. Okay, so after you simplify what we have, it's just become the limit of right, so that become a positive 1. Okay, so that's 1 time, and then you have a absolute values of x minus 1 time absolute values of n is n over absolute n plus 1 is n plus 1, and absolute negative 1 is 1. Right, so we got that. Now, look at these fractions when n approach infinity. When n approach infinity, the numerator and denominator has the same degree, so that's the ratios of the leading coefficient in this case is 1. So your limit now is this approach 1. So we left with absolute of x minus 1 there. All right. So again, using ratio test, this will converges when this less than 1. Okay, so we're going to solve the inequality here. We're going to solve the inequality here to see what values of x that satisfy this inequality. And this is equivalent to x minus 1 smaller than 1 and greater than negative 1. And hence x is less than 2 and greater than 0. Okay, greater than 0. By the way, I didn't say at the beginning, but you should again be able to tell this power series centers at A is 1. So here, the center is at 1. Now that is important because it's going to help you check your work to see if that's correct when you solve this inequality. You see that they have 0 and 2, right? So once I have 0 and 2, I often just draw the number lines and see my interval, right? I'm looking for interval convergence. So you see if we have, we say, 0, right? So that is 2. You see that the 1 is like in the middle, okay, in the very middle of this interval. Now again, from the ratio test, I know that if we have a series, the series will converge anywhere between 0 and 2, okay? Because when x between 0 and 2, this limit is strictly less than 1. Now at the endpoint, I need to do an extra testing, okay, an extra testing. So if you have x equals 0 there, then let's see what we're going to have. If you plug 0 in, then I have negative 1 to the n plus 1, 1 over n, and here's negative 1 to the n. So our series now become, that's negative 1 to the n plus 1, and 1 over n time, here's another negative 1 to the n power. Now this series, you got to be very careful. At first, you might feel, I think that is the alternating series, okay? Because there's this part. But here, there's another negative 10 power. Negative 10 power. So actually, I could combine and rewrite this as, you see, this one times that one, you add the exponents, right? So that's really negative 1 to what? N plus 1 plus n, that is 2n plus 1. And from 1 to infinity times 1 over n. Now think again, this quantity, if you plug in 1, okay, you can write a few terms and you can see. If you write 1, put 1 in, that's the third power, negative third power is negative. You have n is 2, 2 times 2 plus 1 is 5, negative 1 to the 5th power, it's negative 1. Then if you have 3, you're going to have 7 power, still odd power, going to be negative 1. So basically every single term that you've written, if you have written down explicitly, it's negative. So this is a series where you have all negative terms. What if I take the negative, and so you can easily see, right? So this translates into just a negative, right? It's a negative 1. Okay, this is what doesn't matter what you plug in, and it's going to be negative. So if you take the negative sign, it's just 1 over n, and you can see it is no difference than the harmonic series except for the negative values or the negative sum, right? So therefore, I can conclude it diverges. Okay, in this case, it diverges by harmonic series. Okay, harmonic series. Okay. Now let's check the other endpoint. What if x equal the other endpoint is 2? 2. Okay. What if x is 2? Now at the other end, you plug 2 in, 2 minus 1 is 1, 1 to the n, again, 1 to the n is what? It's the 1, right? So I don't think I need to write down. So technically you have 1 to the n, right? 1 to the n is 1. So it just becomes this series. And again, the series, I think I've done that many times. This series converges by, this is again harmonic, but it's alternating. So they don't call it alternating harmonic series. I'm going to write alternating series test. So, okay, so you can use all the series test that. Right, so after we've done the 2 endpoints, what do we conclude? The series now convert between 0 and 2, right? When x between 0 and 2. At 0, it diverges, and that means I cannot include the 0 and then use parentheses. And then at the other endpoint, it converges. All right, so I'm going to include the endpoints too. So our final conclusion is the interval of convergence I is between 0 and 2, including the 2, and the radius of convergence is what? See, distance from here to here is precisely 1. It's precisely 1. Okay. And finally, for number 3, you have n over 3 to the n times x minus 5 to the nth power. Right, so let's check that out. Now for the series, and use this color, ratio number 3. We're going to use the ratio test, a sub n plus 1 over a sub n, and approach infinity using ratio test. And in this case, I have the limit of, I have n plus 1 on the top over n plus 1. Actually, I have x minus 5 to n plus 1. That's supposed to be in the numerator, right? So I can write that like that. And that's 3 to the n plus 1 there, times the reciprocal. Then you have 3 to the n on the top over n times x minus 5 to the n power. Okay, now in this case, what do we have? in terms of cancellation, you see again the powers, there's 2, it become x minus 5 left. I also have a 3 to the n. So 3 to the n and 3 to the n plus 1, there is a 3 left. Okay, so what do we have here? After we simplify, we have it's a limit still and approach infinity. I have n plus 1 over 3. There's an n, right? So I have n plus 1 over 3n time, again, absolute values of this is still the same. And then time the absolute values of the x minus 5 in absolute values. Okay, so we got that, that's left, right? So now if this n approach infinity, what does this quantity approaching? This quantity, this is the first degree over first degree, so the leading coefficient here is 1 over 3, so it's actually approach a third, and therefore our series, so our limit here is 1/3 of x minus 5. Right, so again, for the ratio test, you set that less than 1 and solve for the then solve for x. Okay, so what do we do? Multiply 3 on both sides. We have x minus 5 less than 3. Then x minus 5 is less than 3 and bigger than -3. F5 on all 3 sides. I have 80 and 2 there. Right, so let me go back up here. Now again, now this is a new series, right? What's the center for this series? Series is 5, so that's center at 5. Now I have the intervals down here, and again, the next thing I would do is I'm going to draw the number lines and try to see where is our where's the centers. Okay, so this time let me use this. Okay, okay, so let's see, I have 0 here, 1 2 3 4 5 6 7 8, so here's the 8. So our interval go from 0 to 8. So 3 4, you see that the 5 6 7 8, so 5 in the middle, which is there. Okay, so that's why I call the center. Now if you draw the number lines and don't see the 5 in the middle of the center of the interval, you know that something is wrong. Okay, so that would check the work. Right, so again, so I'm going to check the endpoints. I need to check the endpoints on this interval. Let's do at the 2 first. Okay, when x is 2. What happened is when x is 2, plug in, I have n over 3 to the n, 2 minus 5, that is -3 to the n. Right, so our series would become, right, so I have a different series now. I have -3, what's that again, 3, n over 3 to the n, okay, n over 3 to the n, so I have n over 3 to the n, but then I time -3 to the n. And from 1 to infinity. Okay, and then we can always simplify things when it's come to the special places. You see this too. 3 to the n, 3 to the n cancel, that really left with -1 to the n. So the series would become n times -1 to the n. So essentially, that is an alternating series. Okay, but this is alternating series with the n is 1. If you write it down, it's really 1 or -1, +2, -3, +4. So the alternating series test doesn't satisfy. I mean, doesn't work. Check because the limits of n go to infinity does not approach 0. But so how do we do that? Well, don't forget that the first test is called the divergent test. You take the limits of this, does n go to, does the limit go to, does the limit not equal to 0? That's what we're doing. So to check using the limit using the divergent test, I'm taking the limit of n times -1 to n and n approach infinity. What does this limit? Now, because n is getting bigger, right? 1, 2, 3, 4, 5, 6, 7. This is going to flip the sign from negative, positive, negative, positive, negative, positive. So it's clear that these terms will not approach anything. It go from negative, positive, and getting larger and larger in size. So the limit here does not exist. And because the limit is not equal to 0, so the series here diverges by divergent test. Divergent test. Okay. Now at the other end, if I'm checking at x equal 8, right, what happened when x equal 8, our series now is n over 3 n from 1 to infinity, but then I have 8 minus 5, that is 3, so it becomes 3 to the n. Right, you can see that you can cancel them, and that becomes just n. Oh, that one is easy enough to see. That one is diverges by divergent test as well. When you take the limit of this term, it's go to infinity and it's not equal to 0. So after all, these two say 2 not converge, 8 not converge. So your interval convergence will be anywhere between 2 and 8, not at 2, not at 8. So your final answer is the interval conversion is from 2 to 8, excluding endpoints. The radius of conversion is from 5 to 8, 3. Right? That finished the sections 9.8 power series.